And yeah, well, the talk is a little bit, I have added a little bit something to it which was not in the announcement, and this is due to Jing Song here, because with discussions with him on risk assessment and probabilistic risk design or whatever, he said, oh, you should put something like that in your talk. And I said, it doesn't really fit to heterogeneous materials. But he said, no, it's good to have it in there to have a discussion. So I followed his advice. I throw a little bit else out, okay? And so let me give you a little overview. And I think it stand here. So first of all, why to use heterogeneous random fields? So for me, heterogeneous means also random. Heterogeneous means that we don't really know what the properties, material properties are. And so this is an uncertainty or lack of knowledge or whatever you want to call it. And I find it's not a bad way to model this with probability theory, okay? And then you end up with random fields. And so then what can you do with this? So this is how I'll come a little bit to risk assessment. So you can do uncertainty quantification and other things with this. Then I'll jump back to this random fields, and what I would like to convince you of, and I have a very simple example there, is that all these representations, so we want to then have what you typically want to have to represent a random field, a random process. You want to have independent random variables multiplied by some time functions, spatial functions, or whatever, and when you add them all up, they give a good approximation to your random field stochastic process or whatever it is. Okay, and this is a way to model it, be it Monte Carlo simulation or anything else like functional approximations, which we mostly use here. Still, you have to model the input, and that's the way to do it typically. Okay, and actually, I don't know really many other ways of doing it. And I think they're all connected to represent factorizations of the covariance. The covariance contains practically all the spatial information about such a random field, and then the random variables tell you how often which part and with which probability, density, whatever appears. Okay, and there's a few things which can help us in modeling these things, like if we know certain things beforehand a priori about these fields. Okay, something which had to go out, but what I wanted to talk about, or sometimes we know it has to be a positive, or it has to be a positive definite field. Practically all material properties are in some way positive or positive definite. So like if you think of the elasticity tensor, it's a positive definite tensor because if you multiply it with strains, it has to be the strain energy, okay, and which has to be a positive definite form. And the same is true for conductivity tensors, diffusion tensors, or whatever you have them, okay. And so that's something. So sometimes we know certain symmetries which a thing has. For instance, if something has been laid down, let's say in a natural process which puts layer after layer, one thing I used to work with when I was in industry is sea ice, for instance. I mean, sea ice is formed by little sort of layers freezing onto the bottom or the top usually, the bottom of the ice. Okay, so it has a Planck isotropy, often assumed. Okay, so that's something you know a priori about this, and then how do you put this into your model? Okay, and and the last thing I will just give you one example from. This is also the time's too short to talk about all these things. Is then to use low rank approximation methods. We'll see a little example of what this is to approximate these. Okay. If you want to model a field in 3D, you end up very, very quickly with many, many points which you want to generate. And then you have to think about something on to do this fast. And these low-rank tensor approximation methods are a way of doing it fast. Okay, let me just give a little model problem. I think I've shown this in almost every talk. So this is something where, let's say we want to model the groundwater flow. Okay, and this is a little picture of an aquifer. And so in the simplest case, which I've written down here, the stationary case, this is this diffusion equation. It comes from mass conservation and Darcy's law, and the conductivity kappa is typically not known. Okay, Typically, it's also not the scalar like I've written here, but it's a little tensor. But I just leave this away now for simplicity. Okay. And then the sinks and sources, I mean, it's rain and rivers and whatever, they're typically not known. So these are uncertain elements, and we model them as random fields. Okay. And if kappa, F, and G are heterogeneous random fields, kappa is a material property, other two are loadings or external actions, then of course the solution will be 1, 2, the u of x and omega, the variable describing the state of the system. Okay. And so the first thing is to determine this u depending on the inputs. Okay. So this is a possible realization of this field kappa, generated in these methods that I will explain in a second. This is now once you have all this, what you can compute. For instance, so the first picture, I think, what you see here is, I think, a realization of the solution, and I think is the mean, the variance. And this is, for instance, something you can compute, the probability of solution being larger than some number. Okay? And these are typically the things you'd like to know. These are expected values of some functional of the solution. Or these are typically the things you'd like to know from such a computation. The probability of some event happening. Here it's the event that u is larger than 8. I mean, this is a Mickey Mouse example. 8 doesn't mean anything. It just gave a nice picture. Okay? So... So the whole thing is called uncertainty quantification. If something uncertain goes in, and you want to know the response of the system, and so that doing this computation is called now uncertainty quantification. Okay, and so once we can do this, I've talked 6 years ago, 4 years ago, I don't know, about how to do uncertainty quantification. So I'll not talk about this now. If you don't know how to do it, just think of Monte Carlo simulation. I mean, this is the most expensive way, in my view, to do this, but one possibility is very easy conceptually to think of. So if you don't just think you do Monte Carlo simulation, you do millions of computations, okay? So once you've done it, what you can assess the uncertainty in the output, okay? So that means you can compute something like this. The probability something happens, okay? This is estimating the probability of events. In engineering structures, is maybe the probability of failure. So some of the events may mean your structure is failing, okay? So there would be, for instance, the probability of failure. This is typically not so easy to compute because for typical engineering structure, this is a low probability, okay? And computing low probabilities accurately is not so easy, okay? But again, I will not go further into this. Then once you can do this, what you can use it for is also to identify unknown parameters in your model, okay? There may be some other parameters which are not observable in your model, which you'd like to know. One might be the connectivity, for instance. You might go out and do measurements. Let's say in this example, you drill holes, measure the hydraulic head, and then from that you try to infer what the connectivity really is, okay? One place where this is done is what's called history matching in oil reservoir modeling, okay? So they measure what comes out of their wells. From that, they like to deduce how much oil is down there and what is the permeability, connectivity, whatever, of the rock down there. Very, very tricky calculations because the value on the stock exchange of an oil company typically depends on how much oil reserve it has. And this is something you'll be modeling this way. So you can see that it's a very sensitive subject there, okay? Once you know how to do this parameter identification, then you can plan where best to measurements or what kind of measurements to perform best. This is the optimal design of experiments, okay? And something you can do is perform risk assessment and then design with low risk. And this is the last thing I'd like to talk a little bit further, a little bit more. So if an input into a predictive model like we have here, if it's a random, then the output is a random quantity too, okay? And typically, if you're designing something, you have design variables, which you can change. Okay, you can make some column this thick or this thick, or a hole this deep or this wide, or something like this. So these are design variables which you have, which determine your design. So design or decision variables. And then you have unknown or random variables, which you don't know how they are. You will later meet one realization, and this happens or this doesn't happen. Okay. So, and to each design and realization, there's typically a cost associated with it and a benefit. Okay, and the cost and benefit, one of the things when you hear cost is, of course, you think in money, so that's one thing it could be, but it could be other things. Human lives lost or saved, natural habitat destroyed, groundwater polluted, whatever. So there's many things to think of. I think not all of them are easily converted into money. Some people try and say everything's convertible into money. I don't really believe this, okay? And typically you're interested in the effective cost. So this is cost minus benefit, or the negative of that. This is the effective gain, if you want to see it. And then, okay, one would say we'll make the design to minimize this in some way, the effective cost, okay? There's one problem in practice. So this is very academic to say we will minimize cost to society. And this is, in practice, it really looks really different. In practice, you have different social groups, and the cost and the benefits have different components which different social groups have or don't have, okay? So let's say Cj is the cost to social group J, and Bk is the benefit to social group K. And very often you have decision that one group has a big benefit and the other group has all the costs, okay? You can think of many decisions which are like, and this gives, of course, rise to political conflict, okay? So that is the difficult part about making these decisions, that things are not so simple that you can just minimize some cost or something like that. Anyway, for just to talk a little bit further on, even if you have one quantity only, cost to society, again, I think this is, then it is still not so easy to do, okay? And just let us go for a little moment and think of how is risk defined in engineering, okay? So typically in engineering considerations, this looking at social groups is not done, okay? You just look at one cost, not even the benefits typically not considered, really. So let's say society as a whole, okay, to make it simple. And typically you're interested in engineering, and typically one outcome, the failure, okay? And what you say is that the risk, this is what we call RE, the effective risk, is the cost. Let's forget about benefits. So the engineering risk is the cost of that happening times the probability of this happening. That's the usual definition of engineering risk, okay? And if you have more failure modes, then it's the sum of these terms. And in general, so it would be the expected value conditioned on that you have failure, okay? So this would be termed the risk of decision D, yeah, or design D. And then what you typically die is to minimize RE of D, the engineering risk of D, and this would be a risk-based design, okay? So what it is, it's the expected cost of failure, okay? And, but the problem is that for each design you take, the cost is a random variable, okay? And what engineering risk is, this definition is just assessing this random variable by just its mean value. This is, of course, if you don't know anything else about this random variable, this may be the way to do. But here often we do know much more. Okay, just look at these two examples which I've written down. So imagine that there's 6 outcomes, all with equal probability. Think of a die or something like this. Okay, and -1, so that's a loss. Let's say +1 is a gain, or the other way around. This is a cost, so +1 is a cost, -1 is a gain. Okay, so the first random variable has expected cost 0. Okay, and the second one too. But in the second one you could use $1 trillion. Yeah? In the first one you can use $1. So that's why no one has problems playing lotto, because all you can lose is $1. But something where you bet your house and whatever, even more, then you wouldn't play this game. Okay, so this is why engineering risk, just taking the expected value, is, I think, it's too short. I mean, it doesn't catch what you need to really assess risk. Not that the financial industry does it much better, but they typically take a quantile. They take the 5% quantile, so let's say with 5% probability they are risking this amount. They call this value at risk. And they usually use this to make their decisions. In the global financial crisis, unfortunately, they use the wrong distributions. You know? And then the thing what comes out is wrong too. So they completely underestimated the risk. So I think if you want to do a risk-based design, you have to look at more things just as at the engineering risk. And as this example with these 2 random variables shows is, and this is every observation of how humans behave is that they are risk adverse. They will take small risks, but not, let's say, you will not take the 10 times as large, incurring a 10 times as large loss with 1/10 of the probability. People will not do this. Okay, so this relation, which is inherent in the expected value in the mean, that it's linear, this is not how people behave, and this is not how they decide. Okay, so I think if you're going to do risk-based design, one has to do something different a little bit there. Okay, so quantiles or things may be things to look at. I think there's more things, especially when we can do these kind of computations, we have much more information, and I think it would be silly not to use it. Okay, so much to risk-based design and risk assessment. Okay, just let me go now to what I wanted to talk about more, and this is how to represent heterogeneous random properties. Okay, so just to have notation here a little bit, so we have a random variable, I call it little r, omega is some probability space, and v is the space where we have realizations. Okay, a spatial field, a vector, or whatever you want, just a number. Okay, the expectation we call the first moment, also r bar. Then we have the fluctuating part. This is when we subtract the mean, and an important thing is the covariance. Okay, and so a random field, we can say, is a collection of random variables indexed by some set t. The t may be spatial position, point in time, or whatever you want to have. Okay. And to make it simple, I will always assume here that the mean, the expected value, that it's 0. Okay, you can always add this later on. That doesn't mean anything for the probabilistic description. Okay, an important thing now is this covariance function, which is defined before there. So it's the tensor product, if R is a vector, the tensor product of R with itself, and then the expected value of that. And that contains a lot of information about the process, and is very important for modeling or representing it. So I take a very simple example here. So let's say we have a random variable which can be m different vectors with m different probabilities. Okay? So something very, very simple. And we make it so that the mean is 0. Okay? And now let's put them all in a matrix, column-wise. So this is the matrix X. And then when we take a diagonal matrix, which is the square root of the probabilities are all positive, so I can take the square root. And then I form this matrix capital R. Okay? And then the covariance is just R times R transpose. Okay? And this is really what's happening all the time when you're representing something. You have a factorization, so this R times R transpose is a factorization of the covariance. Okay? And I've written it down there in components. Actually, it's PM times RM times RM transpose. Okay? And because C, the covariance matrix, is a symmetric positive definite matrix, it has an eigendecomposition in orthogonal vectors with positive eigenvalues, actually, because it's positive definite. Okay, this is what I've written underneath there. And because the eigenvalues are positive, I've written sigma squared, because I'll need the square root later on. Okay, so what it's connected is with the singular value decomposition of this matrix R. Okay, so if CR is U sigma squared U transpose, then R is U sigma V transpose, where V is another orthogonal matrix. Okay. And now I've introduced white noise. So white noise is a random vector which has mean 0 and covariance unity. Okay. Then this matrix R times white noise has the same covariance. Okay, and there I need m white noises. I can leave the V at way, by the way, and just take n white noises, and it still has the same covariance. And this is typical for what you want to have. So this, you can say, is a spatial vector. This is a random variable, and this is a factor you multiply it with. This is a random variable unit variance, and this is something you multiply to give it the right variance, and then you add it up, and this is the representation of your process. Okay? And all the representations really look like this, and they are all based on factorizations like we have here, like R transposed. Okay, this is the simplest case here. Okay, think of any other B which factorizes C. Okay, so that B transpose is C. K can be any number. Okay, obviously K has typically to be larger or equal than N, so that you can do this if C is full rank. A frequent choice, most people who do know this, to take the Cholesky factorization. Okay, So this is exactly a factorization like that. Then if you take B times K dimensional white noise, that has the right covariance. Okay. It will not have other properties, right? But it will have mean and covariance will be right. Okay. If you want to have other properties right, you have to work a bit more. One possibility is, which is also related to the singular value decomposition, you define these random variables rho I. So these are the inner product of one of the eigenvectors of the covariance matrix, ui, times the random process, so that's a random variable, and then you divide it by sigma I, which is just a number. Okay, and then it turns out these random variables rho I, they are uncorrelated. The product of two of them, the expected value is either 0 or 1, whether I is equal to j or not. And then R can be exactly represented as this sum. Okay. So I have now a representation of R in n independent uncorrelated random variables. Okay. And these random variables rho R. And this is typically what I want to have. Typically, of course, I want to go a bit further. I want a representation in independent random variables. Okay. And it's a bit harder to do, and I will come a little bit to later. But what we can see here that representations of the random variable R are connected with factorizations of either this matrix capital R or the covariance operator. Okay. Good. Now let me jump a little bit into a bit more complicated things. So imagine we have just an interval from 0 to t. You can imagine time, okay, or it can be one-dimensional space or whatever you want to have. And when we have what's called a wide sense stationary process. Okay, so that's one. If you have something like this, and you have reason to assume that it is that the stochastic properties here are the same as over there or there or there. Okay, this is what you call homogeneous, stochastically homogeneous or stationary. This is a priori knowledge which you have. But this helps you to have these factorizations. In this case, it tells you practically everything. It tells you, for instance, that the covariance only depends on the distance between the 2 points. At which you look at, most people know this here, okay? What does it mean? That means the covariance is invariant against shifts. If you shift both points by the same, you get the same covariance. If you shift your random process, by certainly, it's essentially the same random process, okay? Now, C can be seen, the covariance can be seen as an operator in this integral equation, which we have down here. Before it was a matrix, it's pretty obvious it can be seen as a linear operator. Okay? And what it means to be shift invariant, this means this operator commutes with this translation operator. Okay? Because it's invariant under shift. Now, if two linear operators commute, they have the same eigenvectors. Okay? And the eigenvectors of the shift are very easy to see. If you take them on a real line, the shift is complex exponentials, e to the I k x or something like that, e to the I omega t if you're in time. Okay, these are the eigenvectors of the shift operator. So they have to be the eigenvectors of the covariance matrix. That means I can use Fourier decomposition. Well, these are the Fourier functions. Okay, and right away you see why the eigenfunctions of the shift invariant covariance matrix are the Fourier functions. That means the Cahun-Löw decomposition is the Fourier decomposition. Okay. So if I write down the Cahun-Löw expansion now for such a matrix, I get something like this here, and they satisfy this equation here. The problem comes now. Here's the little problem. That's why most people don't see this connection. That this is essentially the same thing. If you're just looking at a finite interval and compute this eigenvalue problem, and on the other hand, this function c, little c of t, which is on the legs, t is a leg, which is formulated in that, is obviously symmetric, okay, and has a cosine Fourier transform because it's symmetric, it's a symmetric function. Okay, so if I write this down, and then I use elementary trigonometry to express the cosine or the difference of two angles, okay, then I see that this function has an expansion like this, and this is exactly like the one before. And if I go one page back, can see it's exactly like this eigenexpansion. Okay? So, but there's one thing which is not quite right. So this is the spectral decomposition. But the problem is that they are not orthogonal on this interval. Okay? And also the random variables would be correlated. But still we know we can write this like this. And the problem is that we've made a finite interval. And then shift invariance shifts you out of the interval. So you have either to assume that the interval is infinite, but then we know we come to Fourier integrals. If we want to avoid this, we know it's enough to make this interval twice as long. Okay. So there's a little bit classification now what problems and difficulties arise. Of course, if you come to an integral, you don't have discrete eigenvalues. You have a spectrum of eigenvalues, a continuous Fourier transform. So I will not go into this. But if your set T is just n points, then it's simple. It's the first example I have. Then everything is linear algebra. Okay. When we have this, we still have series. We have Fourier series because the operators are what's mathematically called compact. That means they have a discrete spectrum. They have distinct eigenvalues and eigenvectors. Okay. And the other cases, unfortunately, are more difficult. They lead to the sum over the eigenvectors and eigenvectors becomes an integral. Okay. So I will just leave this out and just hint that there is something you can do. It looks formally the same. All the sums have to be replaced by integrals. And in this case, the operators become even unbounded. Okay. So, and then you have to be really careful in which spaces are these eigenfunctions and so on. And this leads to what's called Gelfand triplets or Regan-Hilbert spaces. These are things which were invented for quantum mechanics. They have exactly the same problems there, abstractly speaking. Okay, good. I will just stick with a simpler case here, and just have us look at this stationary issue. Okay. So this is what I was trying to say before. If it has stationary things, let's say stationary just on a set of points. Okay. So if I shift it by 1 point, I essentially see the same thing. Okay. So if I add L to the index, I essentially see the same thing. Of course, this shifts me out of my index set. That's the problem. But if I see on what range this lag has, okay, then it turns out that the lag has twice as big range as my index set. Okay, and this is why you have to double things. I mean, most people know this. They know if they want to do a spectral representation on a domain this size, they have to, let's say it's in 2D, they have to make the Fourier domain 4 times as big, double it into each direction. In 3D, you have to take it 8 times as big. Then you can, because Fourier, of course, on a finite domain is periodic. Yeah? This is not what you want to see in your random field. But if you do everything twice as big and then you take a little chunk out of it, you won't realize that it's periodic. Okay? So this is typically how things are done. This is how all the fields which you see here were generated. Okay? So, which means now this, the covariance matrix here, if we have it for this simple thing, so it was a matrix before, but it has this property that it's invariant under these shifts. Okay? So the matrix, if I look at on the twice as big domain, this turns out to be a more general case. I'll just hint a little bit under it. So these shifts you can see as a group of operations which act on your index set. Okay? And when you double the index set, so you have 0 to n, and then you take the negative numbers down to n minus 1. You have twice as many then. Okay? So you have 1 to n to start with, and then you add 0, minus 1, minus 2, minus n minus 1. Then you can make it periodic. So computation. If you go over n plus 1 is the same as minus n minus 1. Okay. So if you take the shift in this way, it's a group. And when you have such a group operation, then you can look at the eigenvectors of this group operation. Okay. This is exactly what we had before with shifts in the domain. So if I look at the shift operator, I can do this. Once I know this, I know how to do many other cases. For instance, a fractal random field, which is invariant under scaling. If you make everything twice as big or half as long or whatever, it always looks the same. This is also a group of operations. It has different eigenvectors and eigenvalues. But once you know that, you can treat it in exactly the same manner. Okay? So this is, again, I'll just hint this, but this can be put in a very abstract way setting on operating on these groups. Okay? So I've written it down a little bit here. So, and usually we have the group of integers, or the group of integers modulo some number. Okay? But it can be something else too. Okay? So it's best known for the Fourier transform, for which it's typically a shift, but it works for other groups as well. Okay? So this is called in mathematics abstract harmonic analysis. I will not go into it. What I just want to point out, the important thing is that you have prior information which is invariance under some group action. Okay? Either because you assume it or you know the process which generated your material properties was in such way that this is true, or you don't know anything better. That's another reason maybe to assume something like this. Once you have that this is prior information, you can put it into your model. So your model comes out that way. Okay? Good. So this is, I think I'll go a little bit quicker and not go into details here. On this set, which is then twice as big when I enlarge my set, okay, so that everything becomes periodic, then the covariance matrix on that looks like this. And by the way, these here are just copies of the other things there. And as you see, this is always the same sequence of integers here, and then you have the same one is just shifted by one and rotated periodically. Okay, such matrices are called circulant matrices. And the upper part, which was the covariance on our original part, is called a triplex matrix. And typically when people do this computation, it is explained like a linear algebra trick. I take a triplex matrix and I do a circulant embedding. I take this triplex matrix as part of a bigger matrix, which is a circulant matrix. What's good about circulant matrices? This is what we've just seen. Other way, the circulant matrix, the eigenvectors are known. They're discrete signs and cosines. And again, you have Fourier analysis. Okay? So it's the same thing. But it's not a linear algebra trick. It's this invariance under group action. Once you see that, then you see that circular embedding is just a special case of knowing what is the eigenvectors of the group action. And using this, then you already know what are the eigenvectors of the covariance matrix. Okay? And we've seen before in the little example, once we have this, we can do the Cahoon-Loewe expansion, which is a representation of our random field, our heterogeneous material properties. Okay? And here I will not go into this. We see that multiplication by this covariance, by that kind of matrix, is actually discrete convolution. Now everyone probably who's done a little bit of analysis remember this too. If we have convolution, what does the Fourier transform do to convolution? It transforms it into multiplication of the two Fourier transforms. Which means if you look at the things as operator and vector, so the one you convolve with is the operator, the other one is the vector. If you think of a matrix, and a matrix which just multiplies each component by a number is a diagonal matrix. So the Fourier transform diagonalizes convolutions. That means we have an eigendecomposition of it. It's the same thing now from different points. You always see the Fourier functions are the eigenfunctions. Okay? So it's another way of seeing it. Good. And I've written down what the eigenvectors are down there in the last 2-3 lines. So one is all cosines, the other one all sines, and then there's a constant one. And by the way, here the spectrum has multiplicity 2. So each eigenvalue has 2 eigenvectors with it. One's the cosine, one the sine. It's become, because in complex space, it's the exponential, which is eigenfunction, and it decomposes in cosine and sine. And then we have, when we do this here, we have again the Cahoon-Loewe expansion. Okay? So this is what we have here, and this, in this case, it's a discrete Fourier series. Okay? Good. And what we have now, so we have orthogonal vectors here, this UKM, orthogonal vectors, here in this case they're discrete sines and cosines. Before an example, in a very simple example, I didn't make this assumption, there were just some orthogonal vectors, the eigenvectors of the covariance matrix. These random variables are uncorrelated. That's the stochastic term for orthogonal. Okay? And this is how I compose my field. And the thing is now, of course, that you can do now, when you have something like this, Now you can do the simplest kind of low-rank approximation. If you look at the number sigma, so it's just a variant of the Greek sigma, which I've written there. When sigma is very, very small, it's probably something you can drop. You don't need it. Okay. So what you can do here, and this is typically done in this kind of thing, only those random variables which have considerable variance are taken into the computation. The other ones are not important. Okay. And practically all low-rank approximations work in this way. Okay. What is the motto is there? Of course, we do have a PDE to start with, a continuous model which we want to do. We discretize it in some way. We make a little error anyway. Okay. Then we have to do a nonlinear computation with iterations. There's another little error. If the error which comes from the low-rank approximation is in the same order of magnitude, it doesn't hurt us. But allowing a little error here might drop your computational demand by a factor of 100. And that's the important thing. Okay? It's just like with multi-grid or anything like that. It's the same kind of idea. We can allow a little bit of error, and this allows us to do much, much less computation. Okay? And this is what's true for low-rank approximations as well. Good. And now this is the important thing, which I've introduced already in this my simple example. So imagine we have a random field. Okay? And the important thing is, by the way, it's even wider, this concept. The parameter omega doesn't even have to be a random parameter. It could be some parametric dependence. So omega could be cats and dogs or whatever. The set omega is complicated. It's complicated to work with. What is easy to work with is vector spaces in linear mappings. Okay? So we try to convert something which is a mapping from some complicated set omega. Okay? These are the set of realizations in our case here. To something which is in vector space. And we can associate to this a linear map. And this is the linear map. To each vector, it gives a scalar random variable, just by taking the inner product or a vector with this random variable. Okay? That's the scalar random variable. And that's a linear map, obviously. And that's a linear map between two inner product between two Hilbert spaces. Okay? And then we can compute R star times R, or R transpose times R. That's what I had before. And that guy's called the covariance. Okay? So this is what it is. And the analysis, but now I'm dealing with linear maps. All the information which was on this little r is also in the capital R. And there I'm dealing with a linear map. And that's much easier than with some mapping R. Okay? And I have the same information in there. And this is now, by decomposing these linear maps, as I did in the examples before, I can decompose the spatial information. For instance, what you do when you do Fourier analysis, you do exactly like this. You see on this wavelength you have this much variance, of this wavelength you have this much variance, or whatever. This is exactly what you see. So this is the analysis which shows you this here. Okay? When you don't have shift invariance, then you don't have sines and cosines, but you have other eigenvectors which show you this eigenvector carries so much variance, this one so much, and so much. So this is the decomposition you have here. Okay? And of course, the eigenvalue decomposition of C is the singular value decomposition of this D, of this R, sorry, here. And here again, this is how we write this. And from this, we get again the Cahun-Löw expansion of little r. Okay? And the interesting thing is that any other such representation, any other factorization, leads again to this kind of representation. Okay? So here we see, of course, how we do low-rank approximation. I've hinted at it already. We just stop the sums when the sigmas become small enough. Okay? And we can actually see how big the error is by adding up the sigmas which we didn't take into account. Okay? So it's often very simple to see how much of the variance you've taken in there. And so what we have here, again, this is the Cahun-Löw expansion. This is now the fourth time I'm showing it. So that this is not orthogonal on when you do Fourier on the little interval you want it. It's clear because the Fourier functions are the interval twice as big. Once you see this, you can see right away that Fourier decomposition and Cahun-Löw expansion is really is really the same thing. Okay? Good. And this makes it easier actually to model some things. Okay? So for covariance functions, not every function which is only dependent on the distance is a valid covariance function because it has to be positive definite. Okay? And it's not easy to see whether a function is positive definite. But in the spectral picture, it's very easy to see. There's something called Bochner's theorem, and it tells you if something is a positive definite function and shift invariant, it has to be a Fourier transform of a positive function. Okay? So this is the spectral density. Okay, and it has to be positive. So modeling spectral densities is just a positive function. It's much easier than modeling positive definite functions, which are covariance functions. And for many covariance functions, the spectra are known. So one of the things which is very frequent in material modeling is something called the Matthies class. It's a class of function where you can adjust the correlation length and the smoothness. Okay? So it's very important to have also control of smoothness of the random fields which you're generating. And for instance, if you take the Gaussian as a covariance functions, the random fields are going to be very smooth. You just take the exponential, they're not going to be smooth, but you have one fixed non-smoothness if you want to. And the Matthies class allows actually from Gaussian to white noise, which is very non-smooth, to generate everything you want by changing the smoothness parameter. Okay? And so that's a class of functions where the Fourier transform is known explicitly. You don't even have to compute it, you just have to look it up in the book what it is. So this Matthies function is a combination of Bessel functions and I don't know what, polynomial times Bessel function, I think. And so the Fourier transform is explicitly known. You just look it up, you know it. So this whole Cahoon-Loewe expansion analysis is very, very simple to do. Okay. And so this is typically what you start with, for instance, even if you want to do Bayesian identification. And then if you do measurements, the measurements will probably change your covariance, and afterward it's not shift invariant anymore. Because after all, this is only an assumption. Okay, something which is very strongly connected with this. So this is something which really has to do more with classification. It's something called the reproducing kernel Hilbert space. Okay, and so on what you do on the reproducing kernel Hilbert space. This is actually something used for classification, whether you know whether something, an event, is in this set or this set. Okay, you observe something, you want to know is it this or this, and you want to have a classifier. The simplest things are classifiers in a vector space where you can have a hyperplane. Everything on this side of the hyperplane is group A. Everything on the other side is group B, because to see whether something's on this or that side of the hyperplane is very easy. And this is done with reproducing kernel Hilbert spaces. So you choose a kernel. This is this matrix R, or operator R. This gives you a certain covariance, or you choose the covariance and you know which its Fourier, which its eigenfunctions are. And this maps your set, omega, which may be very complicated, cats and dogs, and you don't want to know what is a cat and what is a dog. Okay? Maps it into a vector space, and then you can put a hyperplane and distinguish between these two. And it's exactly the same mathematical theory which is behind that. Okay? Good. So there's more expansions which we can do and to have representation. So the other one is a spectral expansion. So I take now on the spectrum, so this is where I have described my the spectral density of my covariance function. I can take on the spectral density, I take the functions called zeta of omega here, and I can do a representation like this. And this again generates the same random field with the same covariance and the same randomness structure. Okay, there it's not so easy to see which ones I pick, though, and not so easy to do low rank approximations. Good. So enough of these factorizations now, I think. So what we've seen now is that any factorization C in H transpose induces such a series expansion. Okay, so it induces a representation of your heterogeneous material model. And on the other hand, every representation you have is a factorization of the covariance. Okay, and you've seen in the this is something which is also used very often, especially in filter design and things like this, is smooth white noise. So when you go back to the very first example I had, so we introduced white noise and sent it through a linear mapping. This linear mapping is what electrical engineers call a filter. So you filter white noise, and what comes out is something which has the covariance you want. Okay. So this is another way of expressing random elements or whatever, which model random fields, stochastic processes, or whatever. So there's many different ways of doing it. Sometimes, which means this is white noise and then transformed by some mapping. Okay. So you can, for instance, take the PDE, which I had in the beginning. You take white noise at the right-hand side, and then look at the solution of the PDE to white noise excitation. Okay. This is actually a convolution with the Green's function of this differential operator, okay, which gives you then the covariance. So there's many different ways of seeing on how, when you filter white noise, which is essentially a representation like this, a factorization, on how there's many different ways of generating your random field. Good. I think I'll go a bit field forward. So let me spend a little bit here on when we have vector and tensor valued fields. Vector valued fields, I'll leave this a little bit out because there's not much really to say to them, and they don't hardly ever appear in material modeling. Typically we have tensors of even order when we model material properties. Okay, and tensors of scalars, things which are tensors of second order, fourth order, and so on. Okay, and even order tensors can be seen as linear mappings. You see them as a matrix by just taking the indices, tensor indices in two groups, and one on the columns and the other one on, so you can model each of them as a matrix if you want to. And seen as a matrix, they have to be a positive definite matrix typically. Okay, and so this is something where I had to leave out a little bit now because otherwise I wouldn't fit into the time. But the way we model something like this, which has to be positive definite, is we look at its logarithm. Okay, be it a scalar or be a positive definite matrix. You can compute the logarithm through the eigenexpansion. Just take the logarithm of the eigenvalues and then do eigenvalue decomposition, take the logarithm of the eigenvalues. The logarithm is then free. Okay, so you can model the logarithm. See, the problem is that when we model a random field as a sum, a linear combination of independent random variables times some spatial function, we actually do linear algebra. We do interpolation or whatever you want to call it. Okay. This is really only well done on a vector space. If you are on a curvy manifold, this is not the right to do it. So if we say, okay, we meet in the middle between here and Germany, then we think we meet somewhere on the Maldives or something like this, not 5,000 kilometers down in the center of the Earth or something like this. Yeah? So this shows it. If you say something is on a manifold, you have to have some other way of averaging, and it's here too, than just taking the straight line and connecting it. Okay, and positive elements, positive definite tensors, are not a vector space. They're geometrically speaking a cone in a vector space, a positive cone. And this cone is a Riemannian manifold, and you have to do the averaging, whatever, in this Riemannian manifold. Of course, the thing you can do is to map everything into the tangent spaces, do the computation there, and then map it back. And it turns out that the logarithm and the exponential function do exactly like that. Okay? So a straight line mapped with the exponential turns out to be a geodesic on this manifold. So you can do the computation with the logarithms of them, and then take the exponential later on. The exponential, by the way, of a matrix is just a polynomial, so you don't have to sum infinite series. It's the Cayley-Hamilton theorem, okay? So if it's a 3x3 matrix, it's only 3 or 4 terms, that's all you need, and so on. Yeah. So it's actually easy to compute, typically. And what you can make sure also then when you do this is to make sure you model other additional information which you have, for instance, Planck isotropy, certain kinds of whatever material symmetries you have. You can model this on the log of the field you're trying to have, okay, where it's typically subspaces of the space of all symmetric matrices then. All symmetric matrices which have this additional property is typically a subspace, isotropic or not, or something like this. And when you take the exponential of this, what comes out will have the same properties, okay? So in this way you can make, for instance, model random fields, even if you assume that your material is, let's say, isotropic. Not every realization, every point will be. So it's important then to model a random field which on the average is isotropic, but not every realization has to be so. Okay? And these are possibilities of doing this. Good. I think I'll go a little bit quicker now here. So there's one point where these things are very simple, and this is where we have Gaussian fields. Okay? Because then these random variables which appear in these decompositions, which were achieved with some linear transformations, they're also Gaussian. And then they are often uncorrelated Gaussian random variables, and uncorrelated for Gaussians means it's independent. So that's what you want to have. Just to make clear once more why it's important to compute independent random variables. Later on, we want to compute things like we were talking in the beginning, risk, probability of something happened, whatever. These are expectations over these random variables. Expectation is an integral. Okay? You want to compute an integral, I think everyone remembers this from analysis. If you are in some crummy coordinate system, it's very hard to compute an integral. You know? It's already a little bit easier if the coordinates are locally orthogonal, like spherical, cylindrical coordinates or whatever. It's a bit easier to compute an integral. This locally orthogonal means like uncorrelated random variables. But we all know the easiest way to compute integrals is when you have Cartesian space. Okay, and you can compute each direction independently. And this is independent random variables. Okay, and this is why they're important to have for computational purposes. Okay, and if we have non-Gaussian random variables, well, things turn out to be a little bit difficult. Okay, and but what can be done there is that these random variables, which are not Gaussian, can be expanded in Gaussian functions of Gaussian random variables, but of course they cannot be linear functions, otherwise they would still be linear. So the simplest thing there to take is polynomials. So this has a long tradition. It was already done by Norbert Wiener in 1930 or something, 1932. And that's why I call Norbert Wiener's polynomial chaos expansion. Okay? So polynomials is the classical choice, but one can take other things. And then one expresses the random variable as a polynomial in independent Gaussian random variables. Okay? And then you have your decomposition. So first thing is the Caron-Loeb decomposition. You have uncorrelated random variables. And then these that get expanded into independent Gaussian random variables. Okay? And then you have a representation of your random field in independent Gaussian random variables times some spatial functions. And these spatial functions have all the properties which you want to have there: shift invariance, symmetries you'd like to have at a certain point, isotropy, plan isotropy, or whatever you'd like to have for your material property. You can put them all in there. Okay? In this way, the synthesized field will have the properties you'd like to have. So each realization will have certain properties, either exactly the way you design it or on the average, depending on how you design it. Okay? Good. What I'd like to show you is, I think, is a little example, for instance. So this is an example realization of such a random field, and that's where I stopped. And this is actually, so this was some computation which was done to do what's called kriging. Okay, something which is very often done in geostatistics. It's a very simplified form of Bayesian analysis. It's Bayesian updating with the assumption that we know the covariance. Okay? The challenge here, for instance, in this thing was that this cube had 10 to the 15 points, 10 to the 5 in each direction. Yeah? So it's huge. You know, I mean, that doesn't fit on your computer. Whatever. There's very few computers will. That's like, what is it? It's a petabyte. Yeah. So peta, and then that's 8 bytes, so it's like 10 petabytes of memory. Okay. not many computers in the world which have that much. Maybe the NSA has so much storage, I don't know. Universities typically don't. And the thing is, for instance, how do you do computation? I mean, if you try to multiply a matrix with 10 to the 15 times 10 to the 15, if you do it in the trivial way, it blows you out of your mind. So there's no way you can do this. This can be done very quickly, and this has been done like this with these low-rank representations. It turns out, so here there was, again, the assumption that there is a shift invariant field. So we know what the eigenfunctions are, their sines and cosines. That means we have to use the Fourier transform. The Fourier transform, of course, can be done by a fast Fourier transform. That is a low-rank representation of the Fourier transform, if you want already. But it turns out the Fourier transform can be made even simpler. So it can be, again, if you allow a little bit error, so the fast Fourier transform doesn't make any error. It computes the exact Fourier transform. But if you allow a little bit error, you can make it even much simpler. And the computation drops down to very, very few computations. You can do it in your laptop in 2 minutes. Even it's such a huge thing. So this is the power of the low-rank approximation, that every operator you have in there is being approximated in this low-rank form. By allowing a little error. And of course, the dream, which I described before in the computation, so we have a random input and we compute what the random output is, and we compute what the risk is, or I don't know, whatever. Do Bayesian updating with it or something like this. The dream is, of course, that all of this can be done in low-rank representation. You can represent the input like this one in low-rank format. You do the whole computation in low-rank format. You get the output in low-rank format. And I actually claim that if it's not like that, you can't really handle it. Then you can only handle Mickey Mouse examples. If you want something realistic in 3D, it has to be in this way, and otherwise you cannot do it. Okay? So let me show as a last little thing here, a little movie, which comes from actually when we do fluid structure interaction, but which has random fields. So we'll leave this here, and I think it's this one here. It has sound, so you see two random fields represented in different ways. One is the turbulent wind field, which is shown here only on the disk, which the rotor sees, and the different colors. Now again, I'll come back again. I'll put it on loop, I think. And the different colors represent a different magnitude of the wind speed. And the other random field you saw there, by the way, the clouds were not simulated, they were just put in. Everything else is simulated. And let me see if this thing comes back again. The sound was not simulated either. The student added this to me, so it may sound nice. It's coming to the end. Now I'll start again. Yeah. The other thing you see, which is a random field, now in space and time, is the waves. Okay? So they were also generated in this way, actually in a much more complicated way, because the Fourier description of waves is only valid for deep water waves. The wind turbine obviously is on a current in shallow water, so we generate deep water waves and let them run into shallow water where they become nonlinear, steeper, whatever, and then they hit the wind turbine. So this is a nonlinear transformation of such a random field to give another random field to do something. These are not material fields, but these are examples on how you can generate fields. Okay, I think I'll stop here. And thank you very much for your attention. Thank you.